Okay, and we are live. Okay, so I'll take those. Okay. Thank you. Okay, awesome, thank you. Check my inbox. Okay, so for next week, we have an exam. It's on chapters 3, 4, and 5, so that'll be next Thursday. So you need to make sure you bring a calculator because there'll be some metabolic problems from chapter 4 on that. So in preparation for that, you have some helpful documents. So if you go down to the study guides, you have the previous document, chapter 3 questions, and then you have another helpful document here with a study guide for those 3 chapters. So you can begin looking over that material. For today, my goal is to finish chapter 4 and start chapter 5, and then also have a small group activity for us to do. So do you have any questions? Okay, so you're going to need a calculator today. You can use your cell phone application for a calculator, but for the exam you'll need just a regular calculator. So let's go ahead and get in here. So we last left off this slide right here. So you might wonder what the oxygen uptake is for an activity like strength training. So you think cardiovascular type activity, traditional cardio activity, continuous moderate intensity type activity, you can identify with the elevation in heart rate and oxygen consumption. But certainly large muscle group type movements, squats and leg presses, ground-based type movements and so on, you're taking in a considerable amount of oxygen to support those activities because there is a minimal amount of oxidative metabolism during those. Of course, we emphasize mostly glycolytic and phosphagen during those activities, but this particular study, done over 30 years ago now, looked at the oxygen uptake during a typical series of leg press sets, so 5 sets of 6 to 12 reps. And so you can see the VO2, which is the oxygen consumption in milliliters per kilogram per minute. So you can see modest levels of oxygen consumption. These are the averages during each of those sets. So during a certain point, you would expect oxygen consumption to be higher, probably during or just after the last repetition. You'd be breathing with a little more frequency and depth. But overall, as you begin to recover, your breathing rate would drop, the depth of breathing would drop, and so your ventilation would be lower. So this would represent the mean value. So overall, we're talking about 33 to 47% of a maximal VO2. So some people might ask the question, can I improve my VO2 max through strength training? The answer is it depends on what your VO2 max is. So if you're someone that has a relatively low VO2 max, so we're talking maybe in the mid to high 30s in terms of your milliliters per kilogram per minute, then strength training would certainly provide a sufficient stimulus to your cardiovascular system to improve your maximal VO2. If you're an elite endurance athlete or even a college endurance athlete, so I've had Ace and Logan and Bryant. I've done VO2 tests on all 3 of those guys, and those guys are up in the high 60s to low 70s. in terms of their VO2 max. So doing strength training is good for endurance athletes, certainly, but not for improving VO2 max in their case, because they already have such a high VO2 max. It's not going to be stressing their cardiorespiratory system sufficiently to improve their oxygen uptake. So for those guys, strength training is all about improving muscle imbalances and improving efficiency. That we know efficiency is very important for endurance performance. So that brings us to the respiratory exchange ratio. So that's an acronym that you want to memorize. So that's a hint. So that guaranteed that'll be on the exam. So what does RER stand for? And you'd say respiratory exchange ratio. So it's a ratio. It's calculated by taking the carbon dioxide produced divided by the oxygen consumed. And so the reason why this is so important is because it reflects fuel utilization. So we consume oxygen and we produce carbon dioxide. So remember, as pyruvate is converted to acetyl-CoA, and then acetyl-CoA goes through the 8 steps of the Krebs cycle, we produce some carbon dioxide. And so that's the carbon dioxide that we're talking about. Carbon dioxide produced divided by the volume of oxygen that we consume. And this is measured at the lungs. So it has to be, we have to be in a steady state for the respiratory exchange ratio to be valid. Because as soon as we go above the anaerobic threshold, then we're no longer in a steady state. And so the amount of oxygen consumed is not necessarily going to reflect just oxidative metabolism. So the RER equals the volume of oxygen, carbon dioxide produced divided by the volume of oxygen consumed. So remember what the dot over the V represents?
Per minute?
Yeah, per minute. So it's a rate. So we like to use that minute value in exercise physiology. So a total body level, what is happening at the cellular level? So what's happening in the muscles in terms of how much oxygen we're consuming, how much CO2 we're producing, and we're measuring it at the lungs. So a key point, how is it that, excuse me, how is it that we're able to tell how many carbs and what percentage of fats that we're using? And it has to do with the differences in chemical composition. So the amount of carbon dioxide produced and the amount of oxygen consumed will vary based on whether we're using predominantly carbohydrates or fats. So let me show you how this works. So C6H12O6 represents one glucose molecule. So in order to oxidize one glucose molecule, we have to consume 6 molecules of oxygen. So to completely break down this whole thing, completely break it down, produce ATP, we have to consume 6 molecules of oxygen. So on the other side of it, what we get, as we studied before in chapter 2, we get 30 ATP out of that. We produce 6 water molecules, but we also produce 6 carbon dioxide molecules. So this would represent the amount of O2 consumed and the amount of carbon dioxide produced. So the respiratory exchange ratio is calculated by taking the amount of carbon dioxide produced divided by the amount of oxygen consumed. So what would the RER value be then? Very simple, it'd be 1. Yeah, that's right. So if we were using 100% carbohydrates, so in other words, if we're using 100% glucose to fuel a given activity, then the respiratory exchange ratio is equal to 1. Usually, though, it's a mix of carbohydrates and fats, and we'll get into how that works. Say, for example, we're using 100% fat to fuel a given activity. So this represents one molecule of palmitic acid. Palmitic acid is a very common fatty acid. So different chemical compositions. So take a look. So you have 16 carbons versus 6, 32 hydrogens versus 12, 2 oxygens versus 6. So a fatty acid requires a lot more oxygen to process. So in order to break this molecule, this one molecule of palmitic acid, we require 23 oxygen molecules versus 6 molecules to break down this molecule of glucose. So the take-home message is that fat requires a lot more oxygen to process through metabolism. So the RER is going to be a lot different. So to break down this one molecule of palmitic acid, it's a common fatty acid, we require 23 oxygen molecules. So on the other side of it, you remember from chapter 2, one molecule palmitic acid, you get 106 ATP, okay? So we also make some water, but we also produce some carbon dioxide. So can you see how the ratio is going to come out differently? If we're using 100% fatty acids, what's the RER going to be equal to? So you take 16, right? Carbon dioxide produced divided by oxygen consumed, and what do you get? Yeah, 0.7. Okay, so the 100% fat, our respiratory exchange ratio is 0.7. So we can measure that through indirect calorimetry. So as you're taking your VO2 test in about a month, we have all the software that computes the respiratory exchange ratio. So simply based on the amount of oxygen you're consuming and the amount of carbon dioxide you're producing, you can easily come up with what mix of carbs and fats you're utilizing at the moment. So let's take a look. So you just told me correctly that with a respiratory exchange ratio of 0.7, you're going to be utilizing 100% fat, which equates to 4.686 calories per liter of oxygen. 4.686 calories expended per liter of oxygen consumed. So you might be wondering, well, what would my respiratory exchange ratio be right now? So as you're sitting here, respiratory exchange ratio. So baseline RER is generally 0.85. 0.85. So tell me, as we sit here having this discussion together, what percentage of ATP comes from carbohydrate? What percentage comes from fat? Based on the table there. 49, 51. Yeah. So even at rest, we have a certain calorie expenditure. So our bodies require ATP even at rest. And so right now, 49% of resting ATP production comes from carbohydrate, 51% comes from fat. So we talked about the period following exercise. So there's an acronym, EPOC. What does that stand for again? Yes, excess post-exercise oxygen consumption. So an elevated oxygen consumption following exercise in the hours, minutes and hours following exercise, especially high intensity exercise. So what we find is during the EPOC period that our resting or baseline respiratory exchange ratio tends to drop down to about 0.81 to 0.82 during the EPOC period. So what does that tell you about fuel utilization during the EPOC period? Yeah, we're using more fat. So during the EPOC period, minutes and hours following a really hard workout, we're down to 0.81 and 0.82, which means as the RER goes down, the percentage of fat calories goes up, the percentage of carbohydrate calories goes down. Okay. Now, what about during a workout itself? So especially a sprint or anaerobic type workout, short duration, high intensity, what we find is that during a workout, that the respiratory exchange ratio will go up. If it's very anaerobic, so beyond the anaerobic threshold, like interval training where you're back and forth over the anaerobic threshold and then back for recovery, we tend to have a very high respiratory exchange ratio. So, and again, if it's beyond the anaerobic threshold, we can have respiratory exchange ratios that are higher than 1. And so you can see that as respiratory exchange ratio goes up, the percentage of calories coming from carbohydrates goes up until we reach 100%, whereas the percentage of fat calories goes down. So do you get the idea on the respiratory exchange ratio, how it's calculated? So the amount of carbohydrate we produce divided by the amount of oxygen that we consume, and we can tell based on that the percentage of calories coming from carbohydrates and fat. So why does this matter? This matters because during steady state activity, we can calculate calorie expenditure. So that's a key measure that we want to know if, for weight management purposes, so people are wondering, okay, well, how many calories am I expending during this steady state activity? So this is useful information for that. So we're talking about calorie cost. So the more oxygen we consume, the more calories we expend. So that's the way it works. So it has to be steady state though. So this works really well with steady state. We can calculate fairly accurately how many calories we expend. So the calorie cost in calories per minute. So how many of you have looked at the readout on an exercise machine and you see calories per minute? And typically an exercise machine will have you enter what? Your weight. That's right, because for a given exercise intensity, the more you weigh means what for calories? At a given intensity, the greater your body mass, the more calories you expend. Yeah, so that makes sense. So we'll get to that. So let's take this as an example. So at a respiratory exchange ratio of 0.91, and let's just say hypothetically, the amount of oxygen consumed per minute was 2.15 liters. Okay, so the amount of oxygen consumed per minute was 2.15 liters. Respiratory exchange ratio was 0.91. What would be the calorie cost for 30 minutes of exercise? Okay, so let's take this step by step. So first thing, let's go back to our table. So table 4.4 to get the calories per liter of oxygen at this respiratory exchange ratio. So we go back and underline right here. So 0.91, this respiratory exchange ratio, we are expending 4.936 calories per liter of oxygen. So with a respiratory exchange ratio of 0.91, we are expending 4.936 calories per liter of oxygen. Okay, so here again. So if hypothetically, I'm just throwing this number out there. So hypothetically, if our oxygen consumption was 2.15 liters per minute, and we are expending 4.936 calories per liter, and we're asking for 30 minutes, okay, so we could calculate that out pretty easily. So 2.15 liters of oxygen consumption multiplied by multiplied by 4.936 calories per liter, what do we come up with?
10.61.
Okay, 10.61 calories per minute. And how many total minutes? 30, so 10.61 multiplied by 30 minutes, because it's 10.61 calories per minute, multiplied by 30 is how many calories? Yeah, 318.3 total calories in 30 minutes. Okay, so again, if our hypothetical oxygen consumption is 2.15 liters, okay, and we have a respiratory exchange ratio of 0.91, and we can say, okay, 4.936 calories per liter. So we multiply 2.15 times 4.936 to get calories per minute. And then we multiply that number, which was 10.6, by 30 minutes to get our calories in 30 minutes, total calories in 30 minutes. Do you have any questions about how that works? Does it make sense? Okay, all right, so let's keep going. So now you're probably asking, what if we don't know the oxygen consumed per minute? And how often do you know that? Never. If you're not in there on the treadmill, I wonder how much oxygen I'm consuming. You don't know that. So, but what if we do know the metabolic equivalent? So I'm gradually working this in. Okay, so what if we know the metabolic equivalent, which honestly we hardly ever know that either, but we're gonna take that step. We're gonna take this step by step. So we don't know the oxygen, but we do know the metabolic equivalent. So metabolic equivalent is what we call a MET. So that's the acronym MET. So read the definition with me. A unit that represents the metabolic equivalent in multiples of the resting oxygen consumption of a given activity. Okay, so at rest, we consume, on average, 3.5 milliliters of oxygen per kilogram of body mass per minute. So everybody, on average, in a resting state, so right now, you're consuming roughly 3.5 milliliters of oxygen per kilogram of body mass per minute. So that represents 1 MET. So as the MET unit goes up, what does that mean for oxygen consumption? That would mean the oxygen consumption also goes up. So 2 METs would be 2 times 3.5. 8 METs would be 8 times 3.5. So we're talking about multiples of a resting oxygen consumption. So this would represent the resting oxygen consumption. Okay, so how many of you would rather remember 5 calories per liter of oxygen versus 4.936? I would. Okay, so at this point, rather than using these values, 4.686, you see all the way down, it's roughly 5 calories per liter of oxygen is what we use because it comes close enough. So it discusses this even on page 106 in your textbook. So let me just read the quote to you here. So right here, bottom of the first column on page 106, if you know the oxygen consumed during any activity, but do not know the respiratory exchange ratio, you can estimate the caloric value of that activity by multiplying by 5.0 calories per liter of oxygen. The 5.0 calories per liter of oxygen value is very close to the average caloric equivalent and it's easy to remember. So that's the key, it's easy to remember. So rather than memorizing each of these values for every MET or for every respiratory exchange ratio, it's easiest just to remember 5 calories per liter. So if you know how much oxygen you're consuming and you know your body mass, okay, okay? It makes it relatively easy to estimate caloric cost because you just have to remember 5 calories per liter of oxygen. Okay, all right, so you can get out a little, most of you have notes out, which is awesome. Okay, so 8.3 METs. So how would I initially determine oxygen consumption if it's 8.3 METs? So 1 MET is 3.5 mils per kilogram per minute. So if it's 8.3 METs, then I multiply 8.3 by 3.5, right? And I can determine the oxygen consumed for that activity. So you multiply 8.3 by 3.5, and you should get a certain milliliters per kilogram per minute. So tell me what you get when you multiply those together. Say it louder. 29.05 milliliters per kilogram per minute of oxygen. So again, one MET is rest. That's what we're all at rest right now. So right now we consume an average of 3.5 milliliters per kilogram of body mass per minute. So if someone's doing an 8.3 MET activity, then we can say, okay, that's multiples of the resting oxygen consumption. So we can say 8.3 times 3.5, and we get 29.05 milliliters per kilogram per minute. So what else do we have to take into account? Body mass is absolutely right. So we have to divide 29.05 by 68 kilograms. So I have the steps here for you. It's actually times 68 kilograms, excuse me, times 68 kilograms to take in, to calculate in milliliters per minute how much oxygen. So this would be a relative value per kilogram, and we want the absolute value of oxygen consumed. So you'd take 29.05 milliliters per kilogram per minute multiplied by her body mass to get the total milliliters of oxygen consumed per minute. So the next step, there's actually 2 more steps, really pretty simple. We want to convert this into liters. So we just basically divide 1,975.4 by 1,000, okay, to get 1.975 liters of oxygen consumed per minute. So why do we want to convert milliliters to liters? Because ultimately we're going to multiply that value by what value? How many calories per liter? 5 calories per liter. So we want to convert the milliliters to liters. So we just move the decimal place over 3. 1, 2, and 3, and we come up with 1.975 liters of oxygen per minute. Okay, so the very next step, pretty simple. You've got your liters. You know approximately how many calories per liter of oxygen consumed, assuming we're in a steady state. So you get 9.875 calories per minute. So what if this person had greater body mass? How would that affect this value? It'd be larger, because more body mass means more calories expended, because greater amount of oxygen consumed for a given MET value of activity. So, okay. So we're taking this in 3 steps. So we've done the first 2 steps. This is the 3rd step. This step is the most practical. So this one, you'd actually be able to say, okay, if I'm going to do a treadmill workout today, you'd be able to calculate how many calories if you know your body mass, and if you know the speed, and if you know the incline of the treadmill. So here we go. So what if we don't know the MET value? And most of the time we really don't. So, but we do know the speed and incline of the activity if walking or running. Okay. So these metabolic calculations are based on known oxygen cost in a steady state. So we have to eventually adjust for body mass, but we know that at rest, everyone has an average oxygen consumption of 3.5 milliliters per kilogram per minute. We know that with horizontal walking, we consume 0.1 milliliters of oxygen per kilogram per minute for each meter per minute. Okay, so that's the speed. Horizontal running is 0.2, vertical incline walking is 1.8, vertical incline running is 0.9. So these are standardized values based on the speed and grade that we're conducting these activities, running or walking. Okay, so let's take some practical problems. So at this point, as you read this, you should be able to relate a little bit more. So it's really difficult to measure oxygen consumption. It's difficult to really know what MET value, but you can look on a treadmill and say, okay, I have this much of an incline and I have this much speed, and then you can calculate how many calories per minute. So what would be the caloric expenditure for a 68 kilogram individual walking on a treadmill at 10% grade and 3 miles per hour for 30 minutes? So all of you that have done treadmill stuff should be able to relate to this. So that's practical. That's something that you could calculate calories if you are in a steady state. So the first thing we need to do is convert miles per hour to meters per minute. So that's how these equations work, is in metric units. So we need to go with meters per minute. So no matter what your miles per hour are, if you multiply by 26.8, that will convert it to meters per minute. So it doesn't matter, 2.5 miles per hour, 3.54, you multiply it by 26.8, you're going to convert it to meters per minute. So easy to remember. So that's the first thing. So 3 miles per hour multiplied by 26.8 meters per minute. So we're covering 80.4 meters per minute. So that's the first thing. So that's important because that's our speed. That's our speed. Meters per minute is a measure of speed. How much ground are you covering in a minute? Okay, so here's your basic equation. So what we want to know is how much oxygen we're consuming. So once we know that, and if we know our body mass, then we can easily get a milliliters per minute value that we can convert to liters, and then we multiply the liters by, what's the number? By 5, and then we can multiply that by the total minutes, and then we can get total calories consumed. Okay, so here's your equation right here. Milliliters per kilogram per minute, resting component. What's the resting component? So how much at rest? What's our oxygen consumption at rest? Yeah, 3.5 milliliters per kilogram per minute. So the resting component plus the exercise part. Okay, so we may not have a vertical component, but I included it in there anyway. So when we do have a vertical component, such as an incline, we include it. If we don't, then it's just going to be the horizontal component. So taking this problem into account, do we have a vertical component? Yes, we do. So we have to take that into account, because you consume more oxygen walking up a hill than you do on flat ground, right? Okay, so it makes sense. So 3.5 milliliters per kilogram per minute. Okay, so speed times 0.1. Okay, where did the 0.1 come from? Let's back up. Right here. Horizontal walking, 0.1 milliliters per kilogram per minute for each meter per minute. So do we know our meters per minute? Yeah, we calculated that, right? 80.4 meters per minute, because we converted miles per hour to meters per minute. Okay, so speed, 80.4 times 0.1, right? Because it's 0.1 milliliters of oxygen consumed per kilogram of body mass per minute for each meter per minute. Okay, so we do have a vertical component in this case. So decimal grade, what does that mean? How are you going to write that into an equation? So how would you put 10% into this equation if you have to put it in decimal form? Yeah, so it'd be 0.1 would be 10%. Does that make sense? Okay, so 0.1 times the speed. What's our speed? Right here, because we converted 3 miles per hour to meters per minute. That's how the equations work. And then 1.8. So you're like, okay, well, where does the 1.8 come from? Let's go back. 1.8 is right here. Vertical incline walking, 1.8 milliliters of oxygen per kilogram of body mass per minute. Okay, so is everyone with me so far on how this works? Okay, so we got our speed, we converted it. Okay. So resting component, horizontal component, vertical component. So it's going to be 10%, which is 0.1 times your speed times 1.8, because that's the constant. 1.8 milliliters per kilogram of body mass per minute for each meter per minute. So how does this look when we have it all written out? Okay, so you got your resting component, got your horizontal component, got your vertical component right here. So ultimately what we want to come up with is one number, milliliters per kilogram per minute of oxygen. Because then we can work with that based on body mass to get calories, total calories. So you work this all out, you come up with 26.01 milliliters per kilogram per minute. If you have a calculator, why don't you just work through that and see if you can come up with 26.01. If you haven't already done so, I think it's useful for practice. See if you can put those three components together and make sure that you can come up with 26.01. Because that it'll be on the exam, so you need to be able to do it. So the big assumption with this is that we are in a steady state. So oxidative metabolism is the emphasis. So as soon as we cross over into that anaerobic range, we're going to be underestimating calories. So this just estimates calories for aerobic metabolism. So, okay, so was everyone able to get 26.01? Okay, so make sure you're good with that. So we need to take that number and we need to get kilograms out. So how do we get kilograms out of that? We multiply by what? Yeah, so you know your body mass. So we can go to the next slide here. Okay, so we have that number, total oxygen consumption. So we took our resting component, we took the horizontal component, we took the vertical component, we came up with a total oxygen consumption, and now we're going to convert it into an absolute oxygen consumption. So we're going to multiply the oxygen by the body mass to come up with milliliters per minute. So you should come up with 1,768.68 milliliters per minute. And then why do we convert it to liters? because it's 5 calories per liter. Okay, so all we did is just move the decimal place over 3, 1, 2, 3, and we have 1.77 liters per minute. Okay, so going a little bit further, that's the number, 5 calories per liter, so 8.85 calories per minute. So if it's 8.85 calories per minute, we're exercising for 30 minutes, so try that, maybe this afternoon, treadmill, 10 degree incline, 3 miles per hour, and just walk for 30 minutes. And at this body mass, for 30 minutes, you'd be expending 265.5 calories. Is how it works. So what if your body mass was 100 kilograms? How would that affect that number? It'd be a lot higher. Is everybody good so far? Make sense?
So
Okay.
for the exam, what values, like, are we gonna have to know the horizontal walking, horizontal running, all those values?
Nope.
memorized?
You're given all that.
Okay.
You just have to know how to organize it.
Okay.
Yep, so you'll be given everything you need, you just have to know how to solve it. Okay, more practice. So what would be the caloric expenditure for a 68 kilogram individual walking on a treadmill? 15% grade. So we're going up in grade, we're going down in speed, 15% grade, 2.5 miles per hour for 30 minutes. So again, let's walk through it. So 2.5 multiplied by 26.8, there's your speed. Okay. So then here's our equation, resting, horizontal. We do have a vertical in this case, so we have to include it. So if it's 0% grade, then you just don't include the vertical. You just include the resting part and the horizontal part. So if you're just running on a flat treadmill with no incline, then you just wouldn't include the vertical part. Okay, so we've got our speed, we've got our constant for the horizontal part, we've got our constant for the vertical part. How would you write your decimal in this case? Yeah, 0.15, okay. Okay, so you can do that. See what number you come up with. So resting, okay, here's our horizontal part. Okay, so that's our speed times 0.1, remember 0.1 milliliters per kilogram per minute per meter per minute. Decimal grade times the speed times our constant, that's 1.8 milliliters per kilogram per minute per meter per minute. Okay, see if you can come up with 28.29. So once you get past this part, it's really easy. So the whole objective to begin with is to come up with what the oxygen consumption is. Once you have that, then you can easily do the rest. So this PowerPoint is on D2L like always, so you have it there. So should come up with 28.29, make sure you can. So I can get this clicker to work. Okay, so there's the rest of it right there. So there's your milliliters, so multiplied by the body mass. Convert that to liters, move the decimal place to the left, 3, multiply by 5, multiply by the time, 265. How many calories did we expend with the other 3.0 and 10%? Exact same. Really, was it? Mm-hmm. Interesting. So what does that tell us? That's a practical, so you can either go faster at 10% or slower at 15%, and you expend exactly the same. So I didn't realize that until just now. Okay, so here we go, another one. What would be the calorie expenditure for a 68 kilogram individual running? Okay, so we're not walking anymore, we're running on a treadmill, 5% grade, 7 miles per hour for 20 minutes. That's a pretty good workout. 5% grade, 7 miles per hour for 20 minutes. Okay, so the first thing we need is, what's our speed in meters per minute? So we take 7, okay, again, multiply by 26.8. So we get 187.6 meters per minute. So that's our speed. So then we've got our equation. So how would you write the decimal in this case? Yeah, it'd be 0.05. So that's, teaching this class for several years, that's, a student will do everything just perfectly on the exam, but instead of 0.05, they'll just put 5. And so that one thing messes up the entire process. So just make sure that you write the decimal form in there. So, okay, so it's going to be our resting, 3.5, 187.6 meters per minute times 0.2. Okay, so 0.2, again, that's our constant, so we're not walking anymore, we're running. So that's the horizontal component. Vertical component, 0.05 times your speed times your constant. Vertical incline running, 0.9 milliliters per kilogram per minute, per meter per minute. Okay. So does everybody understand how we came to this? Right here. So does everybody understand why it's 0.2? Because it's different if it's running versus walking. Same thing. If it's running, it's 0.9 versus 1.8. Okay, all right, so once you have that, it becomes really easy because what's the next step? We got to go with absolute oxygen consumption milliliters per minute, so we can do that pretty easily by just multiplying by the body mass to get our absolute oxygen consumption per minute. Absolute means independent of body mass. So then what do? We got milliliters per minute, liters per minute. Very simple, 3.36, just 1, 2, 3. Okay, multiply by 5. That's a lot of calories. 16.82 calories per minute. Running on a treadmill with an incline. It's an excellent way to improve your body composition. So 16.82 calories per minute times 20 minutes, and we get 336.4 calories total. So very practical, right? You'd be able to go in, and if you're working on a treadmill, you'd be able to do all this. You know what your body mass is, and you would know what the incline and what the speed is, and you could easily calculate all of this. Okay. All right, so we're going to do this review activity in just a few minutes, but I want to finish off with chapter 4. So do you have any questions about the metabolic equations? It seemed pretty straightforward at this point. Okay. All right, so that will be on the exam. You'll be given everything. You just have to know how to put it in the equations and what to solve for. Okay, so efficiency, the most output for the least input. I like that. It's the definition, page 112 in your chapter. So from a running standpoint, how fast can you run and consume the least amount of oxygen? So you have two athletes, and they can run equally fast, but the one that's consuming less oxygen is the more efficient. So remember the documentary comparing Kenyan versus Danish runners? It all came down to that one factor. It wasn't VO2 max, it wasn't differences in muscle fiber composition or enzymes. They went through that whole big list, and it all came down to efficiency. And it was how the Kenyan runners are built, with really skinny legs. And so they're not expending as much energy to move their legs through each stride. So we want endurance athletes to be like fuel efficient cars. So if the analogy is that oxygen is like gasoline, we want to be burning less oxygen for a given running speed. So the percentage of energy input that appears as useful external work is another way of describing it. So if we look at just simply looking at running form, efficiency, expending fewer calories, making it effortless. Swimming is even more obvious with efficient versus non-efficient. Have you noticed how really good swimmers, it just looks effortless. They just glide back and forth, swimming their laps mile after mile, and then you've got people like me that are just doggy paddling, trying to keep their head above water with their goggles. So same thing with running, good running form. Notice what are some of the differences that you notice here? Posture, right? A little bit leaning forward, just a little bit. The foot contact, okay, mid to forefoot strike versus all of this impact where it's a heel strike where they're getting all of that force transferred up through the knees and the hips. It's almost like this person is trying to slam on the brakes at the same time as they are trying to accelerate forward. So it doesn't work very well if you have the brake and the accelerator going at the same time. Hip flexion, another thing here with greater hip flexion. You're able to push off the ground with a little bit more mechanical advantage here with this foot versus this foot back here. So there's full hip extension here with the ground push off, where the hip is only partially extended in this case. So greatest distance runner of all time, arguably at this point. Just set the world record for the marathon in Berlin last month, I think it was. 2:01 something. But he also broke 2 hours, the only person ever to break 2 hours for a marathon, but it was in a controlled environment with pacers and people to draft off of. But he also holds the official world record at 2:01. So you notice watch how his feet contact the ground. It's more of a mid to forefoot strike. He's got a slight forward lean, shoulders are relaxed. Watch the hip come through as fully extended, a push off. His center of mass is directly over the foot as it strikes the ground, rather than overstriding and the foot being way out here instead of his center of mass. His center of mass is directly over the foot as it strikes the ground. So you look at people that are really good, and then you say, okay, well, there must be something to this, and you try to emulate his technique. Okay, so this is what you would see in a lab, like with our lab on VO2 max. You would see a certain running velocity in kilometers per hour. So that's on the x-axis. And then on the y-axis, this is the amount of oxygen uptake. So you have athlete A and you have athlete B. So at 15 kilometers per hour, so that would be a certain running speed, athlete B is more efficient at this running speed. And why would athlete B be more efficient? How can you tell? Yeah, so at 15 miles per hour exactly, athlete B is using less oxygen for that speed versus athlete A. So that's more efficient. Now, that being said, athlete A has has a higher VO2 max at 70 milliliters per kilogram per minute versus 60. So there's lots of, just like any other sport, there's lots of things that go into performance. Efficiency is one of the most important ones for endurance athletes. Okay, so I want to show you a couple videos. Then we've got Chapter 4 review activity together, and then we maybe get into some of Chapter 5 too. So this first one is on VO2 max.
The United States hasn't won an Olympic medal in cross-country skiing since 1976, but in 2010, several skiers hope to change that. If they're successful, you can be certain it's due to their incredible endurance. As Olympic athletes, trainers, and a sports scientist and chemist funded by the National Science Foundation explain, cross-country skiers are among the fittest athletes in the world.
Has anyone tried that here? I would like to try it. I've never done it. I've never done it. I would love to do it. Is it?
Yeah.
Olympic cross-country skiing is a sport known for pushing its athletes to the limits of human endurance.
You have to be a little bit nuts to want to push your body so hard. Just really push yourself to the point where you collapse at the finish line.
Whether the event is a nearly 1 mile sprint or a more than 30-mile race, these Olympians are considered to be among the most aerobically fit athletes in the world.
Cross-country skiing involves using both your legs and your arms, so almost all muscle groups of your body are being used to ski. That means you have to supply energy to all muscles in the body as you ski.
What supplies energy to muscles? During intense exercise, an athlete sucks oxygen into the lungs, which is then pumped by the heart throughout the body in the bloodstream. When oxygen reaches the muscles, it combines with an enzyme called ATP, the carrier of chemical energy within the cell, to produce muscle contractions, which allows movement. Olympic cross-country skiers can, with practice, improve this biochemical process.
What they've essentially done is train their body in how to be more efficient in taking in oxygen and actually transfer that oxygen to be used at a cellular level in the whole ATP to energy conversion.
But even the fittest of the fit have limits to how much oxygen their bodies can process, a peak measured by what's known as VO2 max.
VO2 max stands for the volume of oxygen that an athlete can consume when they're exercising maximally. So the maximum volume of oxygen that the lungs can actually grab, consume, and send off to the muscles.
At the U.S. Ski and Snowboard Association Center for Excellence in Park City, Utah, athletes undergo VO2 max testing up to 3 times a year, measuring the maximum aerobic capacity. Troy Flanagan is the center's sports science director.
We want to know whether that training is actually effective or not, whether it's increasing the size of their aerobic capacity.
The test is done on a treadmill with the athlete hooked to special equipment that measures volume of air taken in and amount of oxygen consumed and other physiological factors. It's a quick but painful test because it pushes athletes to the absolute limit of their ability to consume and process oxygen.
We can pretty much max an endurance athlete out in about 6 to 8 minutes, which sounds amazing when these athletes normally train for 6 to 8 hours in the woods on snow, so you can imagine how hard this test is.
Liz Stephen, a member of the U.S. cross-country team who did a partial VO2 max test for our cameras, explains how she copes with the pain.
It's a mental game for me. Your body can do a certain amount, and from there, it's up here.
During the test, the treadmill slowly but steadily rises until Stephen hits her max.
Where the yellow line plateaus out means that no matter how much air you're breathing in and out, your lungs cannot consume any more oxygen.
To ensure a true max has been reached, the test continues until the athlete no longer can.
I don't usually remember too much about the last minute. You're kind of just hanging on for dear life, and all of a sudden you're done.
Compared to athletes from other endurance sports, cross-country skiers have on average the highest VO2 maxes.
94 millimeters was the highest one ever measured.
After aerobic training.
I really believe it's just a test, and some people, test really well, and some people don't. And I think for me, I use it to see improvement for myself.
On race day, aerobic capacity is just one of many factors determining which athlete will be able to push to the upper limits of human endurance.
Okay, and here's another one that calculates the how to calculate the respiratory exchange ratio.
Wilkinson from Humber College and the University of Vancouver. In this video, I'm going to explain the respiratory exchange ratio as well as the respiratory quotient. These are two concepts important in exercise physiology. You'll probably want to review some of your basic energy metabolism pathways, such as glycolysis, how acetyl-CoA is formed from pyruvate, the Krebs cycle and the electron transport chain, as well as beta oxidation, in order to be able to understand the underlying basis behind RER. So in this video, I'm going to cover what is RER, what can it tell us about fuel use, the basis by which RER is determined, coming back to our energy metabolism pathways, and the difference between RER and RQ. So the respiratory exchange ratio is a ratio between the amount of carbon dioxide produced by the body versus the amount of oxygen consumed by the body. If I produce 1 liter of carbon dioxide for 1 liter of oxygen consumed, I'll have an RER of 1.0. What this can tell us is the type of fuel we're using to produce ATP. So when we see an RER of 0.7, this tells us that the person is using 100% fat to produce ATP. Whereas if we see an RER of 1.0, this tells us that the person is using 100% carbohydrate. And numbers anywhere between 0.7 and 1.0 are going to be a mix of fat and carbohydrate. And we can use a chart to determine this. So you can see at the very top an RER, and I'll come back to what RQ is in a second. An RER of 0.7 is 100% fat, and an RER of 1.0 means 0% fat, 100% carbohydrate. So take a moment, try this out on this chart. Let's say you get an RER of 0.76. What does this tell you in terms of carbohydrate versus fat use? So if we find 0.76, it tells us that the person is using 19.2% carbohydrate and 80.8% fat. How do we come up with this? Well, let's take a minute to look at reactions that produce carbon dioxide. Which of these reactions are going to produce carbon dioxide? So here we've got glycolysis, beta oxidation, formation of acetyl-CoA, Krebs cycle, electron transport chain. Which ones produce it? So did you come up with, when you take a 3-carbon molecule, such as pyruvate, and it becomes a 2-carbon molecule of acetyl-CoA, we have the production of carbon dioxide. The other place where carbon dioxide is produced in forming ATP is in the Krebs cycle. So you get carbon dioxide, 2 molecules of carbon dioxide per acetyl-CoA produced there, because your 2-carbon acetyl-CoA reacts with a 4-carbon citrate, and there's a series of reactions that eventually leads to formation of a whole bunch of other products, including the loss of those 2 carbons. This is what's going to happen when we start with glucose. Glucose is going to have to go through glycolysis to form pyruvate. And when pyruvate becomes acetyl-CoA, carbon dioxide is going to be formed there. Further on, when the acetyl-CoA goes through the Krebs cycle, carbon dioxide is going to be formed there. So there's a lot of carbon dioxide being formed when you use glucose as the start molecule per amount of oxygen used. Now, if our starting molecule is fatty acid, all fatty acids are even numbers. That is, they have either 18 carbons, 12 carbons, 22 carbons, and when they go through the process of beta oxidation to form acetyl-CoA, there is no carbon dioxide lost. So C18, carbon, eventually becomes 9 molecules of the COA and no carbon dioxide is lost. That's going to mean that for a given amount of fatty acids per amount of oxygen consumed, there's going to be less carbon dioxide flow. So our take-home point, when using fat versus carbohydrate as fuel, less carbon dioxide is produced for a given amount of oxygen used. So let's take this a step further and do an actual example to show you where this 0.7 and 1.0 comes from. So recall RER is VCO2 divided by VO2. And if we take a typical fatty acid, let's take C16, this is its chemical reaction to be able to produce ATP. So to consume this molecule in a series of chemical reactions, 23 oxygen is used and 16 carbon dioxides are formed in the process. So if we do the ratio of carbon dioxide formed to oxygen consumed, 16 divided by 23 gives us 0.7. And this would work out for all other fatty acids as well. Let's do the same thing for a molecule of glucose. So if you take your molecular formula for glucose to oxidize it, 6 oxygen molecules are used, and in the process, 6 carbon dioxide molecules are formed. And you know that anything divided by itself, so 6 divided by 6 is 1.0. And if there's a mix of fats and glucose, well, your ratio is going to be somewhere between 0.7 and 1. And that's what this chart here is going to tell us. Now, you may have been wondering, well, what is this RQ business? So far, you've been talking about RER. The respiratory quotient is something that can be directly measured at the tissue, so that carbon dioxide right at the tissue is measured and the consumption of oxygen at the tissue is directly measured. And to do this, invasive procedures are needed. So if you can imagine, you'd have to have both an arterial catheter as well as a venous catheter inserted right at the tissue. And if you know anything about blood pressure, arterial catheters are very complex in that there has to be pressure exerted to keep the blood in. And so this would only really be done under the supervision of a doctor. So not really practical for us regular exercise physiologists. Whereas respiratory exchange ratio is measured directly at the mouth. So VCO2 and VO2 is measured at the mouth. It's used as an indicator of what is going on in the tissue. We would do this with a pretty simple piece of machinery, a bit expensive, but very simple to operate, not invasive whatsoever. So you'd be able to use a typical metabolic cart. In an upcoming video, I'm going to talk about challenges inherent with using respiratory exchange ratio versus respiratory quotient when conditions are not steady state. RER is great for predicting RQ when things are at steady state. So that is during very submaximal exercise, at rest under normal conditions. It's perfect for that. We get into challenges when there's hyperventilation of some sort, meaning past the ventilatory threshold during an exercise test, or potentially at rest when someone is hyperventilating for whatever reason. So for the most part, RER is a pretty good indication of respiratory quotient, and it's much less invasive. So to conclude in this video, we've discussed what is RER, what it can tell us about fuel use, where it comes from, and the difference between RER and RQ. Like I said.
Okay, so I think we'll end off on this activity for today. Should take you about 15 minutes. So please work together, or you can work by yourself, your preference. You should be able to answer the last 2 questions fairly quickly. First 2 questions, you'll need to have a calculator to work out those problems.
Yeah.
So we'll plan on starting chapter 5 on Thursday.
Doesn't make sense when you're talking about it, let's see if they have.